I'm at the Geophysical Fluid Dynamics Laboratory in Princeton, and we're a climate modeling center. We use data to evaluate our models that I'll talk about in a little bit. I'm in the group or division that has the longest name. We're the Biogeochemistry, Atmospheric Chemistry, and Ecosystems division. And I do a lot of climate, carbon cycle, big picture, global modeling. But our division is diverse. We also have fishery folks, that we call them, and they model fisheries and ecosystems, and atmospheric chemistry folks. So we're very diverse, and that's just my division. We have other groups in the lab also, so pretty much cover every area of fluid modeling. This work I'm going to talk about today is work that I did. I finished up a year ago, my dissertation. As a federal employee, I was awarded the Graduate Studies Program through OAR, where they supported for 2 years my PhD, and this enabled me to continue working at GFDL. I had already been working there, and to pursue my PhD. So that was a great opportunity. And this work is also done in collaboration here with a lot of other folks at GFDL and also at Rutgers University, where I got my degree. So my background is very broad, and my dissertation looks at the Earth system response to a perturbation, essentially. And in this case, the perturbation is a paleoclimate application, which is the closing of the Central American Seaway millions of years ago in the Pliocene. But the work can also be, I do work for future projections of climate and historical as well. So this picture here is a terror bird, this big creature in the back of the slide. And these terror birds were dominant carnivores during the Pliocene, about 2 to 5 million years ago. And they stood just under 10 feet tall. And my kids think they're dinosaurs. But their extinction during the Pliocene, many people believe, has been caused by climate impacts from the closure of the Central American Seaway. So that's an interesting little side bit, but I'm not going to talk about terror birds today. I'll talk about the motivation behind the study, why paleoclimate is important, background on how the Central American Seaway closed during the Pliocene, and proxy data and climate model studies that were used to study the Seaway. My experimental design was that I configured our Earth system model, which I'll talk about the models, to represent different seaway width depths to simulate the evolution of the closing of the seaway. And in doing so, I looked at the impact in a broad range of areas, which you'll see that they're actually all connected though, which is the impacts on ocean circulation, which then drives changes in both climate mean state variability and ocean biogeochemistry and the global carbon, and ultimately atmospheric CO2 concentrations. And finally, I'll wrap up with conclusions and important implications. All right, so why study paleoclimate? Why are we concerned with what happened in the past when we should probably be more concerned with what's going to happen in the future? Well, paleoclimate is an excellent tool for improving our predictions of the future. By using climate models and demonstrating reliable skill in simulating past climates, this gives us confidence in our projections of the future with those models. Also, we have proxy data, and these are natural indicators of climate variability, and these can be biological proxies, physical, chemical proxies. These are from tree rings, isotopes. This proxy data has a long time scale associated with it. It's longer than our present instrumental record that you know from the remote sensing work. So this allows us to study how the Earth system responds to changes on these very long time scales that we're not able to do with our current instruments. And also, it allows us to study natural variability in the climate system, which is important for future predictions, separating natural variability versus the anthropogenic forcings of the future. In Earth history, we've gone over different temperature regimes. This is a picture here of the last glacial maximum, which was about 21,000 years ago, and North America was covered by a lot of ice sheets. Up here is 56 million years ago. This is the Paleocene thermal maximum. Temperatures are about 6 to 8 degrees warmer than present. Studying past warm climates is especially useful for predicting the future because we're projecting increased warming under anthropogenic greenhouse gases. And the Pliocene, which was about 2 to 5 million years ago, is an example of a warm climate. Temperatures were about 2 to 3 degrees warmer than present day, although a lot of external forcing factors are considered to be similar. So it's an analogy of future climate change. And by understanding different processes in ocean and climate and carbon in a past warm climate allows us to understand how they may change in the future. So one pressing question is, how will the ocean circulation change in the future? This is a schematic up on top. This is the cartoon, the historical cartoon of the pre-industrial global ocean circulation. I'm sure you've seen this before, maybe. The red arrows or red lines indicate surface currents. Blue is deep and bottom water currents. And green is areas of the ocean that are relatively saline, and blue are areas that are relatively fresh. And you can see here that the Atlantic meridional overturning circulation is in the North Atlantic. Here, water travels up along the Gulf Stream up to the high latitudes where it cools and sinks. The yellow circles indicate deep water formation regions. So that water cools and sinks, and it starts this overturning circulation in the North Atlantic. And we know that it's sensitive to changes in extratropical salinity fluxes. We have projections that look at buoyancy changes with freshwater fluxes from increased warming in the future. We also know that it's closely tied to interhemispheric heat transports, and that it's also had the impact of abrupt climate transitions in paleoclimate records. The last Intergovernmental Panel on Climate Change report, AR5, our lab did a lot of simulations for. And from that report, we found that the rate and magnitude of the changes in AMOC in the future are uncertain. Models do project a slowdown, but the rate magnitude of that is uncertain. May not be as abrupt as The Day After Tomorrow, which movie was based on the shutting down of the AMOC. But we do run freshwater hosing experiments. We've done a lot of those in our lab. And these are where we input an anomalous freshwater flux into the North Atlantic. So this is simulating the melting of ice sheets. And this changes the buoyancy and slows down the AMOC. And we're able to study what causes the rate and magnitude of change. From those studies, we also know that the connection and link between AMOC and changes in ENSO variability, interannual tropical Pacific variability, are also uncertain. So we have a lot to learn in the future of what may happen and its links to climate. Also, the ocean circulation has an impact on the global carbon cycle. This schematic here is from the IPCC report. This is a schematic of the global carbon cycle. It's important biogeochemical cycle, and our models represent this. I'll talk about that in a moment. But we have different boxes here. These are the carbon stores in the boxes in the ocean. And you can see that the deep ocean is a large store of carbon. And how much of that is going to be taken up in the future under warming is a big question we try and answer. And then we also have a store of carbon also on the land. And the arrows represent the fluxes of carbon between the different components. So we know that the ocean exerts a major control on atmospheric CO2. And to understand that better, we'll know better what happens with CO2 in the future. So to study this, we partition ocean carbon into different pumps, a physical pump and a biological pump. And that's the way in which carbon gets down from the surface into the interior ocean. We know that stratification, layering of the ocean, and ventilation of the deep water to the surface with all the gases, that impacts the sequestration efficiency of the biological pump. So changes in that changes how much carbon can be stored in the deep ocean and how much will be exchanged with the atmosphere. And also ocean carbon interactions and those stores vary on a range of timescales with the which is another challenge in our modeling. From the very short, for minutes to years, from the food chain all the way up to the sediments, which I model in this work. And that's very long time scales, which is thousands to millions of years. So to study the climate and carbon cycle and their interactions and how they feed back on one another, we use Earth system models. You've probably heard of climate models. Well, Earth system models is the term we use to means that we have a climate model and we include biogeochemical cycles. So in our case, at GFDL, our Earth system model is a climate model with interactive carbon cycling between the ocean, land, and atmosphere. So that's basically what our Earth system model is. In fact, the first climate model, couple climate model, was performed at GFDL in the 1960s. So we have a long history of climate modeling. When we model the Earth system, we take a three-dimensional grid of boxes that you see here, and we lay it on top of the Earth. And then in each box, we compute or we solve complex mathematical equations that represents the different processes here, such as volcano emissions to the atmosphere, land use, and ocean heat uptake. And we also model their interactions between the components in the different boxes, the atmosphere, the ocean, and the land. And you can see that the green boxes here is the carbon component that makes the climate model or system model, so that the ocean and land can freely emit CO2 take-up and be a source of CO2 to the atmosphere. And we also use proxy data. We use proxy data and remote sensing data to evaluate our models so that we can predict the past, the historical period, and to see how well our models are actually representing these processes. So we do a lot of work embedding models.
What are the size of the grid?
That's a good question. We have all different sizes of grid. Right now, we just developed a new Earth system model that we have a 1/4 degree ocean, a 1/4 degree latitude, longitude ocean, and a 1/2 degree atmosphere. The model that I'm using today is more of a coarser version. It's a 1 degree ocean that increases up to a 1/3 degree and a 2 degree atmosphere.
So 1/4 degree is like about 25.
Right. Yeah. 1 degree is roughly about 12. Right. So yeah. So the higher resolution you have, you're able to resolve more processes. So we continually develop our models with higher and higher resolution, but this demands a lot of computing resources. So for this work with the coarser model, I simulated thousands of years and I got about 20 model years per day. But when we went to the high resolution model, I would get 5 to 8 years a day. So if you're simulating the last millennium, you have to kind of choose your resolution wisely. So these are proxy records for the Pliocene, which I mentioned was a warm period compared to present day. The top panel shows sea surface salinity proxy from a planktic foram, and the values up top indicate lower salinity, the bottom is higher, and time runs backwards on this axis. Paleoclimate, they run time the other way. So you're going from 2.5 million years back to 5 million years. But you can see that the red is a Caribbean site for the data, and blue is the Eastern Pacific site. And you can see that up to about 4.5 million years ago, sea surface salinities were similar between the two basins. And then after about 4.5 million years ago, they began to diverge in proxy records. The middle panel shows the sand fraction mass accumulation rates of carbonate. Carbonate is a form of carbon in the ocean. And that carbonate can be either dissolved in the water column or buried in the sediment. And this is from also the Caribbean and Eastern Equatorial Pacific. And you can see that up to about 4.5 million years ago, again, the carbonate between the two basins began to diverge, where we had increased sedimentation in the Caribbean. Now, the bottom panel shows proxy data from different sources for ocean temperature. And in this case, the blue is the Eastern Equatorial Pacific, and the red is the West Pacific warm pool. And going back in time again, you can see that ocean temperatures were similar between the West and East Pacific. until about 4 billion years ago. And then the zonal sea surface temperature gradient began. So this data shows that there were large-scale changes in climate and carbon and ocean circulation during the Pliocene. And it's from the surface all the way down to the sediment. So the big question is, what caused this change in the records that we see? And one of the hypotheses, which was mine for my dissertation, was that it was the evolution of the Central American Seaway. So I'm going to mention that the timing is not very precise. So these are estimates, but sometime during the Miocene, about 10 million years ago, the Atlantic and Pacific Oceans were connected via the Central American Seaway, and the salinities were similar between the two ocean basins, as we see. There's also a hypothesis about a permanent El Nino-like state because of the mean state of the tropical Pacific, but that's a little controversial. But sometime during the Pliocene, tectonic plates in that region began to converge. So the water became restricted between the two ocean basins. We see divergence in the salinities. And then we have present day, we have a land bridge in that region. And we have the Gulf Stream transporting water to the north, causing the AMOC and North Atlantic deep water and our general ocean circulation that I showed earlier. And we have tropical Pacific interannual variability, El Nino events, and La Nina events forming. So not only is the timing of the Central American Seaway closure uncertain, but also how it closed. There's different paleogeographic reconstructions. On the left is the early phase of the seaway where we had a very wide opening. And I found about almost 20 modeling studies that simulated the very wide seaway. And they looked at the climate and ocean response. There's also an archipelago model for the seaway closure, and this represented the uplifting of a volcanic arc in that region. So this was where the seaway actually shoaled, became a little more shallow until it eventually closed. And then a peninsula model. This is more of a constricting of the plates and a constricting to a very narrow seaway near the border of Central America and South America. So considering this uncertainty, I ended up doing idealized model experiments or sensitivity experiments where I just changed the seaway configuration, left everything else the same, so that we can actually do a detection and attribution study of what the role of the seaway is on the various areas that I looked at. And I ran 3 open seaway experiments based on these reconstructions, which are wide, shallow, and narrow. And I kept the color scheme consistent throughout, so hopefully you can follow it easier in the results. So I started with a pre-industrial closed seaway, which was just our pre-industrial year 1860 model run. So you can see here, this is South America. This is land in the brown, and we have a land bridge. We have no seaway now. And the blue represents the bathymetry, the depth of the bottom of the ocean, and the arrows are just surface currents. And the stars indicate regions of proxy data that I showed earlier, where we have ocean drilling program sites. And then from that closed seaway, I only changed the model bathymetry to simulate a wide seaway, which is 1,300 kilometers wide. So this was a lot of grid boxes. And this, again, is similar to what the other models have used. So I wanted to use that for comparison. And a 2,000-meter deep seaway. And then I did a wide shallow experiment, same width as wide, but I just shoaled that seaway up to 200 meters to represent the archipelago model. And then finally the peninsula model, where you can't really see it here, but I'll show it a little bit. It's just a very 1-degree grid cell wide seaway. And this was really neat because the numerics of our Earth system model are unique in that we're able to only simulate 1 grid cell wide. Some of the other models weren't able to do this to our knowledge. They needed to have more than 1 grid box to be able to do the computation. So this was exciting to see what just a tiny little seaway caused in the climate and ocean carbon. There's some other novel aspects of this research. The spatial resolution, as I mentioned, in the ocean component is relatively higher than some of the other models. It's 1 degree, but it increases to a third of a degree near the equator. I use the model with, remember how I mentioned the sediment carbon has very long time scales, thousands of years to millions of years. So I took our model output and used it in combination with a steady state carbonate model, box model, so that I could accelerate those long time scales. And we could get the first estimates of the carbonate sedimentation from a SEAWAY. And then also, since we have the Earth system model and the interactive carbon cycle, I was able to quantify how much emissions of CO2 there were to the atmosphere from the ocean and actually get a warming potential, compute that from the model to see what the temperature response would be. All right, so we'll start looking at some of the results. They're going to be in 3 main areas. Like I said, they're all going to be connected at the end, hopefully. The global ocean I started with first, the ocean circulation, because you'll see that that really drives, we found, a lot of the responses in climate and carbon. So going forward, we spun the model up, which means we ran it for 1,300 years before we did our analysis. So this allowed a lot of the long time scales, especially carbon, to come to a quasi-equilibrium. And the analysis looks at open SEAWAY minus closed. So we're always looking at open minus closed and the impact of an open SEAWAY. I used 100-year annual averages, except for AMOC and ENSO, where I used 500-year averages to damp out a lot of the variables in those metrics. Okay, so the present day ocean circulation that I showed before is represented here again. The deep water coming out of the North Atlantic travels across the Atlantic Circumpolar Current, the ACC. It then goes up into the Pacific as a more near surface current and goes across the Pacific through the Indonesian through flow. We typically get about 21.5 spare drops through the Indonesian through flow. A spare drop, all the rivers in the world equal 1 spare drop, so that gives a nice idea of the sense of that unit. Then the water goes into the Atlantic, or into the Indian and back into the Atlantic, and it completes this loop. This is our modern day ocean circulation. And we found that with an open SEAWAY, we actually alter this circulation substantially. With the open SEAWAY, we have a net mass transport through the Central American Seaway for all configurations from the Pacific to the Atlantic. And what was interesting is between the very wide Seaway and the narrow Seaway, we have similar water mass transport through the Central American Seaway. It wasn't that big of a difference, even though we were from a very wide grid down to a 1 or 100-kilometer wide Seaway. Our transport through the Seaway decreased once we raised the sill of the Seaway. There was, however, in the wide and narrow, since the depth of the Seaway went down to 2,000 meters, that's the depth of North Atlantic deep water generally occurs, we did find a reversal in the flow in the bottom 400 meters. So we had an invasion of, or penetration of North Atlantic deep water here into the Pacific in those experiments, which was pretty neat. And in the wide experiments too, we found bi-directional horizontal mass transport through the Seaway, driven by sea surface heights and also by the wind stress curl. So overall, when we open the Seaway, this provides a shortcut for that water that comes up into the Pacific. Instead of going through the Indonesian through flow, it now shortcuts and goes across the Seaway into the Atlantic. Now, the other climate models that looked at this found that a lot of the water goes to the North Atlantic, and this affects the buoyancy because there's relatively fresh Pacific water into the North Atlantic, so this affects AMOC and it weakens AMOC in their models. We found that our water, when it comes through the Seaway, it goes down into the South Atlantic, so we transport a lot of heat and salt down into the South Atlantic. And this significantly decreased our Indonesian through flow, about 60 to 80%. So all that water now is coming through the Seaway into the South Atlantic and continuing around. So we have this different circulation of the Southern Hemisphere. And all the heat and salt that gets transported down to the Southern Hemisphere impacts sea surface temperature and sea surface salinity. So on the left-hand side, for reference, I put the closed or control run sea surface temperature and sea surface salinities. And the maps are all open minus closed differences for temperature, and salinity. And you can see that there's a large increase in sea surface temperatures in the South Atlantic. We had such a large heat flux. That water coming through the seaway warmed in the tropics and then got deposited into the southern hemisphere. So typically here in our control run, we have a net northward ocean heat transport of about a half a petawatt. But with the open seaway now, we actually reverse that heat transport. So we have a difference of about 0.8 petawatts with a southward transport. And we also have, you can see some interbasin differences in the salinity here, where the Pacific is relatively fresh and the Atlantic is relatively saltier. So we open up that seaway, you can see the mixing of water and the evacuation of salt. And this is consistent with the similar salinities between the two basins in the proxy data that I showed earlier. But we found that these water mass characteristic changes, not only at the surface, but we found it all the way throughout the depth of the ocean. And this significantly impacted density in the ocean and ultimately the meridional overturning circulation. So I talked about the Atlantic, or the AMOC, the overturning in the North Atlantic. This is the meridional overturning circulation for closed and each of the open seaways. So this is the equator here, and we're looking at the northern hemisphere here, southern hemisphere on the other side, and the pink is a clockwise circulation. So water near the equator travels up toward the high latitudes, cools and sinks. So this represents the AMOC, or a clockwise circulation rotation. Near the South Pole, we have Antarctic bottom water that sinks down near the southern hemisphere, and then it upwells near the equator and creates a counterclockwise loop. So these are our overturning cells. And we found that when we open up the seaway, with all of the heat and salt transport, we changed the density, and we actually reduced the northward extent of Antarctic bottom water. You see in the closed simulation, this goes up to about 40 north. We actually suppressed this northward extent now. And this allows North Atlantic deep water to penetrate deeper. Right? Once we pull that deep water out, it allows the North Atlantic to penetrate deeper and become slightly stronger. This is a time series of the maximum AMOC strength in spherodrops. And you can see that it's only about a 2 spherodrop increase in AMOC, but this is very different than what the other models have shown. And ours is really driven by the southern hemisphere deep water changes in response to the transports. So, and this is supported by most recent proxy data. Originally, the proxy data showed that North Atlantic deep water was a lot weaker in the Pliocene, but they had new data points in the South Atlantic. And this is different ocean drilling program sites of Delta 13C, which is a proxy for ocean circulation. And this is 5.2 million years ago. This is before the seaway closure and after the estimated seaway closure. And you can see that North Atlantic deep water was similar to and frequently stronger than present day, which is these thick arrows here. So, so our results are consistent with this most recent data, and it's very interesting how the different models simulate the deep water at overturn. So to wrap up the ocean circulation part, we found that independent of the stage of shoaling of the seaway, while the patterns were pretty similar, it was really the large-scale ocean circulation changes, and not just AMOC, which was a focus of a lot of the other climate models, that drove changes in the ocean mean state and the properties globally. The seaway actually provided a shortcut. So instead of going through the Indonesian brood flow, the water now went through the seaway and into the South Atlantic. And this transported heat, salts, and impacted the overturning, which we found was slightly stronger. And North Atlantic deep water penetrated slightly deeper because of southern hemisphere deep water changes, which is interesting and has important implications for climate. So the second part will be climate mean state and interannual ENSO variability. I'll just give you some highlights from the results of this. So I mentioned the ocean heat transports. We reversed ocean heat transports. We have a lot of heat now in the southern hemisphere. So this is a 2-meter air temperature difference between the wide seaway and closed. I didn't put them all in here because all the patterns are similar. But you can see that we have a lot more warming now in the southern hemisphere surface air, up to 8 degrees near the Ross Sea. And we also have a little bit of slight cooling in the northern hemisphere. So there's this bipolar surface air temperature response. This was found in other models also. However, our response was different in that we have more heating in the southern hemisphere than the warming in the north. So we have an overall warming with the seaway of 0.7 degrees, where other models all found a cooling with the seaway. And on the right-hand side, you can see the precipitation rate differences, where blue is wetter, brown is drier. And with the increased global mean temperatures, we expect an enhanced hydrological cycle. And we do find that with our model. And we also have a slight southward shift of the intertropical convergence zone, that band of precipitation in the tropics. That usually shifts toward the warmer hemisphere. And we do find that it does shift slightly south here, where we have more rain driven up there. It's also most apparent in the Atlantic and Indian Oceans, but we do simulate that. Other models do simulate that as well too with the SEAWAY.
The 2-meter air temperature, is that the 2 meter above?
Right, above ground. Yeah, so it's a surface air temperature.
Okay.
Yeah.
And how did you get those information from satellite?
This is the model. These are all model results, right? But these are to give you a sense of what the differences are. They are pretty substantial. 0.7 doesn't seem like a lot, but it's comparable to projections of temperature increase under increased greenhouse gases in the future. The top is what I just showed, but the bottom is RCP 2.6 minus closed. And RCP 2.6 is an emission scenario of increased greenhouse gases in the future. We run our models with these emission scenarios, depending on how much mitigation there are. And this is one of those scenarios of increased greenhouse gases. And compared to pre-industrial, we find about 0.8 degree warming for this particular scenario. So this is on the order of the warming that we are projecting in the future under one scenario. And there's also, again, with global mean warming, you expect an enhanced hydrological cycle, and the future emissions also projects that as well. But however, the interesting thing is, even though the global mean patterns are similar, the regional differences are very different depending on what's driving the climate change. So in this case, we have a geological forcing to the climate by changing the bathymetry of the ocean. And down here, we have greenhouse gas forcing, changing the climate. And you can see that the patterns are opposite. You have warming in the northern hemisphere, cooling in the southern hemisphere. So this has important implications for understanding not just the global mean, but that the regional patterns may be different depending on what's driving climate forcing going forward. So this has implications for future work and also for paleoclimate studies. And the tropic mean climate, or tropical Pacific mean climate, is an area of particular interest because variability in this area of interannual ENSO variability leads to El Niños and La Niñas. And in the future, we're really interested in what's going to happen in the tropical Pacific and ENSO going forward. The top panel shows sea surface temperature from the model, and the bottom shows the depth of the maximum DT/DZ, which is the vertical temperature gradient. So that's basically the depth of the ice of the ocean, of the vertical temperature gradient. And in present day, we have usually colder in the East Pacific, right? And we have warmer in the West Pacific warm pole. So this is going across the Pacific. So we usually have this gradient. And we also have a deeper thermoclimate in the Eastern Equatorial Pacific and a shallower thermoclimate in the Western Pacific. And when we open the seaway, you can see here from the differences, we have increased cooling in the East Pacific and increased warming, and also the thermocline further deepens in the east and further shoals in the west. So you can see that when we open the seaway, we have basically an enhancement of the zonal sea surface temperature gradient and thermocline slope in the Pacific. So we do alter the mean state in the Pacific. So the question is, how will that translate to changes in ENSO? And on the right-hand side now, these are absolute values, not just to confuse you, but so that you could see the patterns better. And again, this is sea surface temperature and the thermocline depth. And this is at 110 west. So this is a slice here in the Eastern Pacific. So we're looking at a slice of it going from 2 south to 2 north. So right across equatorial sea surface temperature gradient and their thermocline slope. And the black dashed line is the present day or control run. So in present day, we usually have this asymmetry in sea surface temperatures in the Eastern Pacific about the equator, where we have warmer temperatures to the north of the equator, and it's a little bit colder to the south. So this asymmetry. When we open the seaway, we actually break down this asymmetry about the equator. The temperatures become a little more symmetric about the equator. And many studies have shown that this influences the power spectra of the annual cycle of tropical Pacific variability. We also see, too, that we have a deeper thermocline as expected with the changes in temperature. So if we take a look at the 500-year sea surface temperature anomalies in the Niño 3 region of the Pacific, this is the power spectra for the 500 years. And this is the mean spectra scaled power on the right. Black is the observations, and the red is the model. And the top is closed, and these are the 3 open experiments. So to understand this plot, you can see that at 1, we have this big spike. So this is the annual cycle of sea surface temperature anomalies in the Pacific. And you can see that this decreases as we open the seaway. And we also, as we decrease the annual cycle, the power gets shifted to the semi-annual at a half and the interannual here. And you can also see that from the time series a lot clearer as well. We take power from the annual cycle and we kind of shift that more to the semi-annual and interannual cycle. So this implies that we have increased ENSO magnitude with an open seaway. And a lot of that power shifting has to do with that asymmetry about the equator in the tropical Pacific. So this has implications for looking at how that's changing future scenarios and how ENSO may change. Because we know we have regional impacts from additional El Niños and La Niñas. If we have a larger magnitude of that, there may be more impacts regionally, drought, and so forth. Okay, so for the climate mean state, we found that it's opening the seaway leads to about 1 degree warming. And this is dominated not by changes in the buoyancy flux, but it's dominated by deep water changes in the southern hemisphere. Changing the deep water in the southern hemisphere can significantly impact climate up to 1 degree. And this is comparable to the increase in greenhouse gases. Regional fingerprints of those changes, though, can be very different depending on what drivers are forcing climate change. And that's particularly important to look at in the future climate projections of what's driving those forces, volcanic, greenhouse gas. We have a lot of different drivers we put in our models. And the Eastern Equatorial Pacific, we have the reduced asymmetry in the sea surface temperatures about the equator. And this drives changes in the power spectra of interannual tropical Pacific sea surface temperature variability. All right, so moving on to the last part is the ocean biogeochemistry and atmospheric CO2, because this was really the exciting part of this work. Because, almost 20 other groups did this work, but had an Earth system model. I think there was only one group that looked at the carbon impact, but they didn't have a fully interactive carbon cycle model. So this was exciting to see what we were going to get. And I mentioned that changes in ocean circulation impact global carbon. And this is a plot of annual mean ideal age of the ocean. So this isn't a physical property. The ocean doesn't really have an age, but this is a tracer we put in our model. And this tracer represents ventilation, which is basically how that deep water, the time or the residence time in which that deep water makes it to the surface and has implications for exchanging gases with the atmosphere. So on the top is the closed pre-industrial run at different depths. We have 500 meters on the left and 2,049 meters on the right. So now we're in the ocean looking at ventilation. Purple means it's relatively older water, so there's less ventilation, stays down near the bottom more. So we always have, older water in the Pacific. It's deeper. It takes longer for the water to get to the Pacific and the blue. And we have relatively younger water in the Atlantic and also in the Southern Ocean too, because we have a lot of mixing in the Southern Ocean. Brings up a lot of stuff on the bottom. So when we open the seaway, this is a difference between just that narrow, tiny one grid cell wide seaway and the closed run. One thing you can see that at both depths, we have more orange brown color. So our ocean gets younger. So we have increased ventilation in the ocean. And this has a lot of implications for carbon on different time scales. As I mentioned earlier, there's a lot of different time scales for carbon. The increased ventilation can actually reduce the efficiency of those pumps that I talked about, the biological pump, bringing carbon dioxide from the surface down to the bottom and sequestering carbon. If you have increased ventilation, you're going to reduce the efficiency of that pump. So that carbon's going to stay near the surface longer and escape to the atmosphere. You can also alter nutrient uptake efficiency, and the aqueous solution of CO2 in the ocean has many different chemical species, one of which is calcium carbonate, and this affects the calcium carbonate patterns, which I mentioned earlier can be dissolved in the water column or buried and locked down on thousands of time scale. And this also ultimately impacts atmospheric CO2, changing the calcium carbonate in the deep ocean. So let's take a look at the nutrients and productivity. So NO3 nitrate is a macronutrient in the ocean, and that's on the left-hand side. The right-hand side is net primary productivity. So this is all the little organisms, the critters in the ocean. They take up the dissolved inorganic carbon in the ocean and accumulate biomass. That's how they eat. So on the left-hand side, you can see there's high concentration in our control run in the Eastern Pacific. This is a prime area of upwelling of nutrient-rich waters, and also in the Southern Ocean, which is down here on the bottom. There's a lot of nutrients there. Like I said, there's a lot of ventilation. You're bringing up a lot of nutrients from the deep. For net primary productivity, since we have a lot of nutrients here, they're going to take advantage of it, and so we're going to have a lot of productivity in the East Pacific. But it always doesn't match. It's not always corresponding. You see, the Southern Ocean doesn't have too much productivity, and that's because they can either be light limited, you need light for photosynthesis, or iron, and there's different limitations. I found that ocean biogeochemistry very complex. But when we open the seaway on the bottom, we do find changes in the surface nitrate concentrations and the surface net primary productivity. And this is from the sequestration efficiency of that biological pump. So we reduce that efficiency of pumping down into the deep ocean, and we also reduce the nutrient uptake efficiency. So overall, we have a decrease, or we have an increase in surface nitrate concentration. And you can see up in this area, we have an increase. This is where the ventilation changed, so that the nutrients may stay near the surface longer. And we also have overall decrease in net primary productivity, 5%. And this is because we're not able to sequester a lot of that dissolved inorganic carbon into the deep oceans. We're not able to have that much productivity as we did without the seaway. And this all stems from the ocean ventilation changes. So this is going forward with changes in ventilation and stratification of the ocean. How will it impact nutrients and activity of the ocean and ecosystem? So I mentioned earlier the ocean exerts a control on atmospheric CO2, and ultimately we're interested in the whole big picture. So this is the atmosphere-ocean CO2 exchange, basically the flux of CO2 from the atmosphere and the ocean, where blue represents CO2 into the ocean, and red is CO2 into the atmosphere. So you can see with the upwelling, the deep CO2-rich water, the CO2 escapes the atmosphere in the Pacific. So we have the ocean is a net source of CO2. And also in the Southern Ocean, we also have a net source of CO2 to the atmosphere, again, from that Southern Ocean mixing. When we open up the seaway, there's several different changes in the carbon, but the one noticeable one here is because of the ventilation changes, the North Atlantic switches from a net sink of CO2 to a net source of CO2. So the spatial pattern is related to the ventilation changes. And we calculated the reduced efficiency of that sequestering of the biological pump. We found a decrease in remineralized dissolved inorganic carbon with the seaway. That's because we're not able to sequester that down in the deep ocean. And it was significant. It was about 240 gigatons of carbon, if you remember the schematic from before of all the different stores. So now that we're not able to sequester that CO2 into the deep ocean, that CO2 is freely available and it escapes to the atmosphere via ocean outgassing CO2. 240 gigatons of carbon. Also, the calcium carbonate spatial patterns do change, which were actually consistent with the proxy data that we showed earlier about the carbonate sedimentation and dissolution. So we see a net migration from Atlantic to Pacific calcium carbonate of 150 gigatons of carbon. And because of the long time scales, we actually store an additional 200 gigatons of carbon in the calcium carbonate sediments. And this releases CO2 to the atmosphere. I know it's not intuitive. If you're burying it in the ocean, why is it going up into the atmosphere? But because of the carbon species partitioning for the aqueous chemistry solution of CO2, when you store more CO2 in sediments, you actually shift the equations the other way, so you release CO2 to the atmosphere. So this is a large amount of CO2 to the atmosphere. This is the time-integrated atmospheric CO2 flux. It's after 4,000 model years, so I ran these experiments out for thousands of years. This is the closed simulation, and this is the integrated flux of CO2 to the atmosphere with control run or pre-industrial. You can see that the time scales are very long, and this really isn't in equilibrium. This is why we see quasi-equilibrium. The carbon has very long time scales, so there's always going to be a slight drift. But you can see there is a substantial difference with the narrow seaway. At the end of 4,000 model years, we have this difference here of 500 gigatons of carbon. From all of those different carbon processes I talked about, we release 500 gigatons of carbon to the atmosphere. So that's about 250 ppm when you convert gigatons of carbon to CO2. And that's a lot of CO2. In fact, it's comparable to the cumulative emissions of CO2 since year 1750 to present day. All the CO2 that we've accumulated in the atmosphere is about 545 gigatons of carbon. So that's pretty comparable to that. So and this is just the very narrow seaway. This was what was interesting. That one little grid cell wide opening the ocean changed the ocean circulation such that there's large changes in carbon. And it's important to understand how these processes work on long time scales. And then we found, since we had an Earth system model, we can compute how much CO2 goes to the atmosphere. And we know it's a greenhouse gas, and it warms. So based on some of the metrics, we're able to compute a warming potential of 500 gigatons of carbon. And we estimate this to be about 0.4 and up to a degree warming just from the carbon released to the atmosphere. So this is in addition to the physical climate warming that we saw also. So to summarize the carbon, it's really the changing in ocean ventilation that reduces the efficiency of the pump. So we're not able to sequester a lot of deep ocean. And this also affects spatial patterns of the nutrients as well. We found that there was reduced remineralized CO2 or DIC in the ocean and also increased calcium carbonate burial. Both of those ends up sending CO2 to the atmosphere via outgassing CO2. So those are two very important processes to understand future climate changes with ocean ventilation. And also the cumulative carbon emissions with the SEAWAY contributed to about a 1 degree warming, in addition to physical climate warming that we saw in part 2. So to put this all together and wrap it all up, we found it's really the large scale ocean circulation that changes the climate and carbon, and not just the ANOx changes. We found that the coupled ocean atmosphere dynamics in the tropical Pacific, granular variability, and also carbon is sensitive to circulation changes in the ocean. And that has important implications for future changes in ocean circulation under increased greenhouse gases. And also the regional fingerprints of those changes are starkly different depending on the drivers of climate change. So this is an important reference point of caution too when using proxy data to look at changes in the past. And also it provides an alternative perspective on how different those regional changes may be if drivers other than increased greenhouse gases were driving the forcing that we see in climate change. And also just the ventilation of the ocean has a substantial impact on atmospheric carbon. And this partly hindered sequestration of CO2 and the calcium carbonate burial will release CO2 to the atmosphere, about 250 ppm. And that contributes to a 1 degree warming on top of the physical climate response from the SEAWAY, which was so overall we found a 2 degree warming with an open SEAWAY in our model, which is consistent with the warming Pliocene from the proxy records. But I do want to caveat that this is on time scales of 500,000 years or less, because on these super long time scales over 500,000 years, the effects of weathering and volcanism actually return CO2 to sort of the equilibrium state. Medley of one.
So my immediate question is there any changes going on?
Right now, yeah, they have been talking about digging, another channel through the SEAWAY, for commerce. So yeah, maybe I should look into that and see if I need to.
Talking from the perspective of the impacts, we could see.
Your question also, and also ask to see if anybody has questions.
Yeah, sure. Because looking at the impacts, these ocean circulations can bring in to the hydrogen.
Right.
That surface, or a bunch of stuff I can see.
Right. There's other stuff I haven't
other
even
stuff,
looked at. Right.
Yeah. I imagine, the near term, we could see any, kind of like changes.
Right.
That you have seen in your results. And the other thing I was thinking was like whether there has been any other study that looked at Indonesian through flow, as you know.
Yes, there have been several, because that was about the same time too. The Indonesian archipelago was changing.
Is that credible the hardened region for South Asian monsoon?
Right, exactly.
And I'm always thinking about impacts, because when you're looking at the impacts on hydrometeorology or food or vegetation, it's all over them. Right. And you have talked about all those important regions that are impacting, the food, the ocean productivity, as
all
fish and
So yeah, I know how we looked at the Indonesian archipelago. Yeah, in this study we didn't, but there have been other ones that looked into those changes as well. Okay. Yeah, and that's why this was a nice experimental design, because I was able to just attribute the Central American seaweed changes. Then you can use that in combination with other studies. If you want to put together the pieces of the Pliocene and unlock the mystery of why it was so warm, but there's been a lot of stuff. And in addition, the Drake Passage too. I think it was much earlier, 50 million years ago or so. The Drake Passage was closed. So loop of the ACC in the southern hemisphere, which made a very big difference in climate. Some of my colleagues have done that work as well.
Interesting. Yeah. Is there anyone online with a question for Lori?
Hi, my name is Mia. Hi, Lori. Thank you for your presentation. Hello?
Sure.
Yeah, we can
Yeah,
hear you.
yeah.
Okay. Thank you for your presentation.
Thank
I
you.
would like to know, because it was interesting that you brought up the Panama Canal and how it increases the ventilation.
No, not yours. They have to do it.
Oh, please could you reduce the volume a little bit? And we will be able to.
Is this better?
Oh,
Yeah.
much better.
Oh, awesome. Okay. I noticed you mentioned something about the Panama Canal and how it increases the sea ventilation from the Atlantic to the Pacific Ocean.
Right.
Right. And do you see any correlation between the building of that Panama Canal and, let's say, the onset of different drastic changes in the climate?
The drastic changes in climate with the current building, you mean, of the canal?
That's correct. Just when it was built versus before it was built.
Right, yeah, I mean, that's a good question. I haven't really looked at that, in fact, because again, that's a little hard to isolate what climate change is caused by the building of that canal, but that's an important question. And that would be pretty interesting. But from a modeling standpoint, I haven't looked into that at all.
But the locks is not really free flowing.
Right, they do have locks, so it's not like what we're seeing here where it's the change in the ocean circulation.
Okay.
But they do end up building, again, like they say, digging further up the farms.
Okay, thank you.
Is there any other question from the people who are online? Okay. Do we have any questions? No, yeah.
So do you think that it would be this of tropical storm happen?
Oh, that's a good question. One of the proponents about the, everybody's trying to find out what causes warmth of the Pliocene. And one of the candidates is an increase in tropical cyclones mixing up a lot of the ocean. I haven't looked at that in this model. We do have a cyclone model that I could look into, but I haven't part of this. But maybe that would be interesting to see. You know, again, more heating, right? So you have more energy available for convective activity in cyclones.
It also might develop, right? And they don't have that many like on the Caribbean.
Right. Yeah.
Some of that much heat.
Right. Or yeah, even how the patterns have changed between typhoons and tropical cyclones in the Atlantic. Yeah, that would be neat to look into.
Yes, I just wanted to know for the future simulation, do we look at the fresh water coming from north? Do we also consider that in the future simulation? Because there is actually weakening thermohaline circulation happening when Arctic Ocean comes into the Atlantic, and then we have actually more freshening water.
Right.
And then it's going to actually impact the SEAWAY interaction.
Right. So are you asking if we consider that
Yeah.
in our future projections
Yeah.
under increased greenhouse gases? The melting of Greenland?
Yes.
Yeah, there's actually a big project they're working on that right now. I haven't personally done that, and I don't know if anybody in my lab is working on that. I think it was Andre Schmittner had mentioned that he was interested in looking at that. I don't know of anyone in my lab looking at that right now. I'm sure somebody maybe, but no.
But would you assume then that that the melting in Greenland will affect somehow the deep water?
Oh, of course. Yeah. No, there's implications from this research for that as well, right? Because you know, if you're melting the water, you're increasing the stratification of the ocean, and therefore you're changing the ventilation. So
Yeah.
I think there would be substantial impacts. I think we may need to revisit some of the future projections, looking at some of these areas, especially the carbon impacts and how it affects atmospheric CO2. The last IPCC assessment used Earth system models, I think, for the first time, really. It was the first time the Earth system carbon models were included. So there's a lot of room going forward of what we can do now in further exploring.
Yeah, I was confused by the competing effects of carbon sequestration in the oceans. Because obviously you're sequestering it, you're drawing it down, but then if I have this right, you're increasing the saturation of the water, so then it goes back into the atmosphere.
Right, yeah.
I would think it having equilibrium, but it would have to be lower carbon in that atmosphere because you had to draw
You
down
would
the
think,
carbon
right,
first.
because there's a partial pressure
Yeah.
between the ocean and the atmosphere, but it actually has to do with the set of equations for dissolving CO2 in the oceans, bicarbonate and carbonic acid. And so when you shift, if you add, if you take calcium carbonate and take that away and put it into the deep ocean, you shift those equations the other way. So you go from the ocean to the
Okay,
atmosphere.
so there's another process.
There's another
another
process,
chemical
yeah.
equation.
Yeah, there's several equations, yeah.
Different.
Yeah, because I struggled with that in the beginning also. I didn't understand that.
Yeah.
Yeah.
Yeah, thank you.
Hope you liked it.
Great.